Problem 6. For some integer n greater than 4, a convex polygon has vertices v1, v2 and so on up to vn in that cyclic order. All its edges are the same length. It also has the property that the lengths of the diagonals v1, v4, v2, v5 and so on up to vn minus 3 vn, vn minus 2 v1, vn minus 1 v2 and vn v3 are all equal. For which n is it necessarily the case that the polygon has equal angles? It seems natural to start off by looking at some small polygons to see what happens. We'll start with the smallest valid case, which is that of the pentagon. We're told that all the sides have equal length. We're also told that some of the diagonals have equal length. Here are two examples, the one from v1 to v4 and the one from v3 to v1. These diagonals create two triangles, v1, v2, v3 and v4, v5, v1, which are congruent side, side, side. As a result, the angles at v2 and v5 are equal. By drawing similar triangles for other angles, you can tell that in fact, all the angles of the pentagon are equal. Let's move on to the next case, the hexagon. In this case, the diagonals which have to be all the same length are the three diameters. That's v1 to v4, v2 to v5 and v3 to v6. You can imagine bending this configuration a little so that it looks like this, like a triangle v1, v3, v5, with extra vertices added on the perpendicular bisectors of the edges, all the same distance outside the edge. The symmetry in this picture is enough that all edges are of equal length, and also enough that all the diameters are of equal length. However, the angles are not all equal. The angles at odd vertices are smaller than the angles at even vertices. In fact, a construction like that will work for any even number of sides. For example, we could make an irregular tengon which satisfies these conditions by taking a regular pentagon and adding extra vertices on the perpendicular bisectors of the edges, all the same distance outside the edge. The symmetry in the configuration means that all the edges are the same length, and also that all the diagonals that we're interested in go between one of the original vertices of the pentagon and one of the new vertices added in, so they're all equal too. That settles it when n is even. Now we'll look at what happens when n is odd. All our examples so far have angles alternating between two values, a big angle and a little angle. We'll prove that holds in general. Let's consider a polygon, and we'll look at 5 consecutive vertices of it. We're told that all the edges are equal, and we'll also use that the diagonals v1, v4 and v2, v5 are equal. I'm going to draw in the edge v2, v4 to make things easier. Now I want to persuade you that the triangles v1, v2, v4 and v5, v4, v2 are congruent. They have one shared side, which is v2, v4, two equal sides that are edges, and two equal sides that are diagonals. That means that the corresponding angles of these triangles at v2 and v4 are equal. Also, the triangle v2, v3, v4 is isosceles because it's got two of the edges as sides, and so it has equal angles at v2 and v4. Adding these two pairs of equal angles together, we get that the angles of the polygon at v2 and v4 are equal. But then the same argument will show that the angle at v6 is equal to the one at v4, and that the angle at v8 is the same as the one at v6, and so on for every other angle around the polygon. We haven't used yet that n is odd. If n is even, then we've simply proved that all our examples look like the ones we drew earlier. They have angles of alternating size. However, if n is odd, then if we go around the polygon proving that every other angle is equal, that'll show they're all equal, because we go around proving that v2 is v4 is v6 is v8, but then when we get to the end, we loop around and do the odd numbers. We show that v1 is equal to v3 is equal to v5, and they're all equal to the ones before. So in the odd case, the polygon must be regular, whereas in the even case, it need not be.